of this and you put T1, 0 to L, check it out, you will get that answer. Yeah, or maybe I can write it for you in 2 steps. You get this as T2 minus T1 by L times X plus T1, 0 to L. Now substitute and see what you get. If you put L, this becomes T2 minus T1 plus T1, which is T2. If you put 0, this simply becomes T1. So this result is log of T2 by T1, and rest of it remains same, PAL by R times T2 minus T1. Okay, so let's look at this, what is called as the equipartition. Now before that, did we talk about most probable velocity, average and RMS, etc.? RMS we have talked about while deriving kinetic theory of gases. Average and most probable we haven't talked about. Okay, let's see this. See, we are not directly doing, so we have something called Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution of molecular speeds. See, we are not getting into why it is so, we are just looking at the final result. There is this Maxwell-Boltzmann statistics. Based on this and observation, we get this, that the speed of molecules in gases is distributed like this. It's a bell-shaped curve like that, and what it means is there are a very few at any given temperature. This is at any particular temperature. Not all molecules have the same speed. Okay, that's obvious to you because evaporation happens. Evaporation means what? Some molecules which have greater speed, they move from the liquid phase to the vapor phase. Now they do so because they have more kinetic energy. So naturally everybody doesn't have the same amount of kinetic energy, the distribution. But what is distribution like? Very few of them will have very low speeds. Very few of them will have very high speeds. Most of them will have some speed which is in between, and the greatest number will be having some speed here. Now that speed is called the V most probable. MP, I'm putting the symbol there. V most probable. If this distribution comes up, so based on the statistics, certain derivations are there. We are skipping that, we're directly coming to the result. The results are so, we already know what is VRMS. VRMS equals under root 3 RT by M. So also we have V average, which is under root 8 RT by M, and we have V most probable under root 2 RT by M. So if you notice, the formula for all of them are almost same except the coefficients. Here it is 3, this is 8 by pi, this is 2. And if you say this is like RAM, you can remember that as an acronym. So, and that is in the descending order. 3, 8 by pi 2. RMS is greater than V average is greater than V most probable. Now this result we can use anywhere. So we are not derived it, we are simply taking it from Maxwell-Boltzmann statistics. Okay. So with that background, we proceed ahead. So many times some question might come up that what is the average speed or what is RMS, because any one of them is the calculation is almost the same. Only thing is you have to multiply of 3 by 8 by pi 1 by 2 depending on the question. Suppose you are doing most probable for oxygen, what will you substitute capital M as? Yeah? 32. If you are saying SI units, you substitute 32 10 to the power minus 3 kilogram. Okay? So take care of that. Alright. Let's proceed further. Have you taken these formulae? I'm rubbing this off. So now we move on to what we call as equipartition energy theorem. Another theorem based on Maxwell-Boltzmann statistics. Again, we are not proving it. We are going to apply the result. Equipartition of energy theorem. The theorem states that for a gas in thermodynamic equilibrium, the energy per degree of freedom per particle, the energy per degree of freedom per particle is half kT. The energy per degree of freedom per particle is half kT. Equipartition of energy theorem states that for a gas in thermodynamic equilibrium, the energy per degree of freedom per particle is half kT. Yeah, have you taken that? Now, some of these phrases are new, which is what I'm going to explain. Once that gets explained, you will be able to understand that theorem. So first of all, let's start from the most simple. What is K? K is called the Boltzmann constant. And Boltzmann constant happens to be nothing but the gas constant divided by the Avogadro number. So that's what the K represents here. T is obviously temperature in absolute scale. So the answer for this will be in, R is 8.31 joules per mole per Kelvin divided by 6.0 to the 10 to the power 23, the Avogadro number. Your answer will come in joule per molecule per Kelvin. So one gets that answer. Some people call this as the gas constant per molecule. Joule per molecule per Kelvin is a unit for this. Then, what is thermodynamic equilibrium? It is a single term for three different equilibriums which exist if they coexist. One is thermal equilibrium, mechanical equilibrium, chemical equilibrium. Now, when we're talking about a gas, thermal equilibrium means the temperature must not go on changing. Different parts of the gas, whatever temperature they have, they continue to have that. If you have more than one temperature, then that continues to be that temperature. Because if temperature is varying, the temperature flow will happen and temperature will keep on varying during the observed time. So when you say equilibrium means every portion, whatever you are considering, will have the same temperature. That's thermal equilibrium. Mechanical equilibrium, you talk in mechanics, net force is zero, net torque is zero, which means your gas is not accelerating somewhere, nor is it tumbling. There is no angular acceleration as well. Most of our questions will not have that, but just to be safe, we are saying so. Chemical equilibrium means rate of forward reaction equals rate of reverse reaction. The definition for chemical equilibrium, what does it mean for us is the composition of the gas doesn't change while you are doing the question. Whatever gas it is, it continues to remain in the same chemical state. So these three equilibrium have to be ensured. Mostly you will have them in your questions, and then a single term for all the three is thermodynamic equilibrium. That's how we say. Then we come to the most crucial aspect here, which is called the degree of freedom. Let's write down degree of freedom. We'll be symbolizing it by F. Degree of freedom, write down, is the number of independent variables required to describe the motion of a system or a particle. Okay, now let's understand this. Suppose you are about to catch a train and you are late, and so anybody, if you ask where is the train, they must say it's gone. 20 minutes ago it left the station. So if somebody said 20 minutes ago it left the station, or it is say the train is 10 kilometers from here, because the train has to go down the tracks. So if you go with the average speed of the train for 20 minutes, you will find the train there. They can tell you by this time, the concerned person can tell you where the train would be exactly. So that is because the train is traveling only on the tracks. The train has no independence, but one independence, it can go along the track, that's it. It has 1 degree of freedom. Unlike a car, suppose there was some taxi which was standing there and you say, there was a taxi here, where did it go? You say, we saw it go about 10 minutes back. But now where has it gone? Where has it gone? It can go anywhere. It can go any distance in X, any distance in Y. So X and Y, you have 2 degrees of freedom. You can say X and Y, or you can talk in terms of on the board how many degrees of freedom I have. When I'm writing here, I can move anywhere on the board, but I can't move in space here. I don't have the z degree of freedom. I have x and y, 2 degrees of freedom. When you use your mouse in the computer terminal, what do? You move your hand like that. So when you are moving your hand to and fro, you are moving x and y coordinates, and the same thing gets electrically signaled to the cursor there. The cursor also moves in 2 degrees of freedom. 2 degrees of freedom you have, but if your pet parrot got lost or it flew from the cage, it can be, you don't have to, it may be anywhere. It might be perched on any tree, x-axis, y-axis, and can go up z-axis. So a parrot can fly and you have 3 degrees of freedom for the parrot. It can be in any x, y, z coordinate. So now I'm talking about 3 degrees of freedom. Suppose you're traveling, can you tell me, a ceiling fan has how many degrees of freedom? 1, that's all. It can only spin a particular omega. You can say so many RPM is the speed of the fan. And if you have said it everything about the fan. What about a table fan? How many degrees of freedom it has? Yeah, it can also, a table fan goes like that. It can swing also, and it can rotate also. The rotation has got nothing to do with the swing. The swing is independent of the rotation. So swing is 1 degree and rotation is another degree. That's 2 degrees of freedom. When you're climbing on the staircase, how many degrees of freedom you have? Now, seemingly, there is x and y coordinates in motion, but if you choose your y, the x is fixed. It has a particular slope. Y equals x tan theta. So if you choose to go that much up, you got to go that much forward. So actually your x and y are not independent of each other. If you choose your x, you have chosen your y and vice versa. So basically there is 1 degree of freedom while going up the staircase. Okay? Let's not worry about shuffling on the same stair here and there. Broadly speaking. Okay? Is that okay? So, broadly this is the idea of degrees of freedom. But for example, the human hand has many degrees of freedom. In a single finger also you can either rotate it or you can perch it. You can ask somebody to come like that. With fingers you can make so many gestures because the fingers various motions are possible. Not only fingers, you have fingers, you can move your fingers, you can move your wrist, you can move your elbow, you can move your arm, and you can move it in different ways. So the deaf and dumb have a whole sign language based on how they move their fingers. So what is your 26 alphabets in English become their gestures based on their hand symbols. So if you can generate a language from your hand, must be that a hand has many degrees of freedom. Compare that to a robo looks very stupid because the degree of freedom is not very much. Even if you ask a robo to pick up a pen or something, it simply goes X and then Y, then Z. It goes in a very limited fashion. Okay? So, now what are we looking at? As far as we are concerned, we're talking about gas molecules, monoatomic, diatomic and triatomic. There, how do we look at degree of freedom? See, a monoatomic gas, when we take monoatomic gas, we will consider it that the gas molecule is too small. That's what we assumed in kinetic theory of gases. It is too small, it can move in the X, Y or Z coordinate, that's it. It can spin, but its spin won't be taken into account because moment of inertia for a spherical body is I is 2 by 5 mr square. But if you say r is tending to 0, the moment of inertia is also tending to 0. It doesn't make any sense. So we drop a rotational idea for it. So monoatomic, we will say 3 plus 0, just to emphasize there are no degrees of freedom in rotational motion, only 3 translational motion. That's all. Diatomic gas. Diatomic gas, for example, we talk about oxygen, you could think of it like that. Now, although I made the oxygen so big, but this radius is supposed to be tending to 0. I made it big just to distinguish it. So when you talk about its, well, this too has 3 degrees of translational motion. It can move anywhere X, Y, Z. The dumbbell can move anywhere. The oxygen dumbbell. It's a oxygen molecule made up of 2 atoms with a bond distance of this much. But its spin along this direction will not be counted along the x-axis, along the bond axis, because this moment of inertia will be negligible. But along this axis, it will be there. Along this axis, it will be there. Just like a translational motion can be resolved into x, y, z components, likewise, a rotational motion can also be resolved into x, y, z components. So here, the x component to which we resolve, this is gone for the same reason, because moment of inertia along the x-axis, we will take it as 0. Other two will be there. So out of 3, 1 is gone, so you got 2. So for rotational motion, you have 2 degrees of freedom. As a whole, you got 5 degrees of freedom for diatomic gas. Triatomic, 3 for translational, 3 for rotational, 6, that's it. Except special case or exceptions. For example, if you talk about carbon dioxide, now it's a triatomic molecule, but it's a linear molecule. So its rotational moment of inertia along the x-axis will not be counted. So again it becomes 3 plus not 3 but 2 equal to 5. So this functions like this. But that's just to say exceptions. Now that's the idea. As far as we are concerned in physics, we will just take it as monoditri is 3, 5, 6. Now, just to let you know that there are other possibilities. For example, an oxygen molecule is diatomic, could be vibrating like that. Now this degree of freedom we haven't considered, nor are we going to consider, but these are possible. So that chemistry investigates into that. We will stop ourselves saying, okay, some more degrees of freedom could be there. It is basically a degree of freedom. As far as this equipartition of energy theorem is saying, is what? You can think of degree of freedom as a pocket. Now, usually, I would say a shirt has 1 pocket and a pant has 2 pockets and that's it. We got 3 pockets. Something like that. That's not true for the current wear today. People have pockets all over the trousers. I understand that. But if you consider that, okay, you have 1 pocket and 3 pockets, like currently I'm having about 3 pockets. So if you think I have got 500 rupees in 1 pocket, and if I have 3 pockets, then the total money I will have is 1500 rupees. Because each pocket on an average will have 500 rupees. That is the idea of this equipartition of energy theorem. More the number of pockets, more will be the energy, because average energy in each pocket is same. That is the idea. So we will take these values as 3, 5, 6. That's all. Let's proceed further. What do we mean by the internal energy of a gas? Let us now talk in a different, from the microscopic concept, let us see what is internal energy of a gas. Now, according to the EET, if a gas has F degrees of freedom, then energy per particle will be